All right, welcome everybody to Fine Tuning Fridays with Oxen.ai, where each week we try to take an open source model and put it to the test against some of these closed source models in the ecosystem and see if we can train a better, faster, cheaper model that you can actually run yourself. And one of my hot takes over the past couple months, maybe not so much of a hot take if you've been paying attention, is that I feel like a lot of the big labs want you to think we're on this big exponential intelligence curve. And I actually think we're starting to get to the top of an S curve. And I think a lot of the open source models are starting to intersect right at the end of that S curve. So open source is becoming a really viable option today, and we're going to see it come to life in this workflow that we're going to be showing you. Specifically, we're going to be using this model called Qwen-Image-Edit and cut inference costs from 46K to 7.5K compared to Nano-Banana or like a chat GPT image gen. Um, this particular workflow, we were tasked with generating 1.2 million images in this image editing fashion. So the client had a product catalog of a variety of desks and furniture and cabinets, and they are currently rolling out 14 new color swatches, and you can kind of pair these color swatches together. So, for example, if you have this desk here, and the customer wants a green frame and red drawers, they want the image gen model just to automatically apply the green frame here, the red drawers here, make sure that it looks like a realistic 3D render. Um, and you'll see some of these images even have like stuff on the desk, stuff on the drawers. So it's not as easy as just like generating this with CAD. And even if you were going to do that, it would still be pretty time consuming if it wasn't automated. So they decided to take one of these open source models, Qwen-Image-Edit, and fine tune it on this task. So that's what we're going to be talking about today. And unfortunately, Daniel, the client who we're doing with this with, couldn't make it today, but he gave us permission to like go through the data sets, look at the fine tunes, look at the ins and outs, and talk about how he really saved a bunch of money for his customer. And then we also have one of our partners on the back end, Baseten, on the call that can help us talk through how we actually scaled up the infrastructure to generate these 1.2 million images. So the math behind that is there's 14 color swatches, 14 by 14 is 192, and then there's 6,000 different SKUs in the furniture catalog. So 192 times 6,000, 1.2 million images. And that's a huge compute workload that we have to run through. And so Base 10 kind of specializes in being able to deploy these open source models at scale and run them quickly. So before I dive in, I know we have Raymond from Base 10 on the call. Raymond, do you want to introduce yourself real quick?
I'm Raymond. I lead training here at Base 10. One of the interesting things we think about a lot is capacity overall, and then also how we think about the model development lifecycle overall. And so what we really wanted to do was build a training platform that kept inference in mind. And we've built an infra platform that keeps on-demand availability as a priority across all of our workflows. And so Greg and Base 10 or Oxen and Base 10 have been working together for quite some time now, and it's just really awesome to see the synergy between the two platforms because I think what we have is really complementary, and we can kind of get into how things scaled out as we talk through this.
Awesome. Yeah, and I just want to highlight like a couple things as we were working through this project. So the client had to iterate through, he said 12 different versions of the training data set to get this correct. And even within the iterations on the training data set, he was testing different hyperparameters of the model. I saw at one day, I think he had like 10 different training runs running at the same time. And Base 10 takes care of just like acquiring all that compute and the clusters that we need. And then Oxen takes care of all the software layer, the data sets, etc. And so before he was kind of like spinning up RunPod or Vast AI and managing all these things himself and having to worry about, okay, what jobs do I have running right now? When do I have to kill the machines? And with this like combo of Baseten and Oxen, we spin those things up, spin those things down, and you can kind of run it in your sleep and not have to worry about managing the deploys or managing the data sets themselves. So really fun. It's been fun working with Base 10 and seeing uh, all the access to the infrastructure they give us. Cool. So let's dive a little deeper into the task. So the customer in this case is called Allium AI. They specialize in applying AI and machine learning to understand product catalogs at scale. So anything from like apparel to groceries to furniture. They run computer vision to extract things from labels. They run image generation to generate product catalogs. Um, and today we're going to be talking about this furniture use case. And so the first thing I kind of asked them before we dived into this is like, why can't we just do this in CAD? Like, don't, isn't this a company that has CAD models for all of these things? And he was like, they do, but they don't have like an automated workflow to generate all of these. It would kind of be like hand rendering everything. And then some of the images are actually pretty complex. So they might have like items in the drawers. They did like a real photo shoot for the first set of SKUs, and they just don't want to go and do a photo shoot again for this. And if they can make an automated way to generate these images, that would just save them a bunch of time. So uh, we kind of put our brains together and said, this seems like a great task for image to image models. And if you haven't played with these models, some of the more popular ones are like Google's Nano-Banana or Black Forest Labs has one called Flux One Context. There's Qwen-Image-Edit and Qwen-Image-Edit Plus. So we had a few to choose from. And the first thing that we kind of started with was like, can Nano-Banana do this task? Because it's kind of all the rage right now, all the hype. And so the idea is, can we come in and take, yeah, let's take this like super noisy one and say, change the frame to red and change the drawers to green or something like this, just to get a feel for how well this works. And yeah, we even got a comment in the chat here that don't get the most consistent outputs with Nano, and we'll definitely see this with a few examples running through, maybe like a 66% success rate. I'd say that was about what the client got as well. And we can see our first failure here of like, it definitely did it for this one, but for some reason it decided to add actually, it didn't even do it here. It didn't change the drawers to green. It added a completely new item here. Like we want these things at the exact same angle with the exact same colors. And this was a pretty complicated one, so maybe we'll give it an easier one like this desk. Um, and let's also make sure that the aspect ratio stays the same because that might have been part of it. Um, And so we ran through this with Nano-Banana, we ran through this with ChatGPT image gen, and I'd say like 50% of the time, maybe a little lower, it would nail it. Like that's almost there. We've definitely got a red frame and green drawers, but like this part isn't quite there. And if we take a look at the different colors that the client wanted, is actually a very specific color palette. And we need to nail these colors exactly. So it needs to be like flame red or ultramarine blue or gentian blue. And so you need to make sure that this is like the exact blue of the SKU, and this is the exact red of the SKU. So some of these models, luckily, do let you pass in more than one image. So say we add like the exact red that we want, and say that we pass in like the exact blue that we want. Um, cool. Let's see if given this context, the first one we got was like a slightly off blue and a slightly off red. Let's see if Qwen-Image-Edit Plus or some of these like multi-image edit models can do this. And Daniel asks, given the color swatches as JPEG versus SVG, does that make a difference here? It's a good question. Didn't do too many experiments on the actual compression that we used at all, but I would suggest using PNGs to make sure that you have minimal compression. But even here, like this is Qwen-Image-Edit Plus, but you can see still not the red, still not the blue. So promising like first steps, but definitely not all the way to the quality that the client needs. Um, with like some prompt engineering, they did take the actual names of the colors from here, like flame red and gentian blue, instead of just like a generic red and a generic blue in the prompt. And the combination of that plus this color swatches actually got them much closer. And he started to bootstrap a data set of like, I think it was 100 examples to get started. And we're just like, okay, now we have a data set. Now we have a task. Let's just see if like a quick fine tune can do anything to see if at least it can get like a couple of the pairs before we kind of scale this up to a production level.
And Greg, I kind of
Yeah.
want to jump in here just from like a process perspective and having seen a ton of clients go through like this, what I'll call like the fine-tuning journey. One of the things I really love about the Oxen platform here is just kind of how intuitive and easy it is to sample and assess a model from the start to see what you can do with prompt tuning, to see what you can do with the base models. Because I think a lot of people reach for fine-tuning before they understand where the baseline is. And I think that's a huge part of the iteration journey. It was like, let's see what Banana can do. Let's see what Qwen can do out of the box. Let's see what we can do with prompt tuning. And then now you get to the, okay, how far can we push it with fine tuning?
Yeah, totally. I would actually recommend you always start with prompting, even if it's just to like define the problem better in your head, and understand where the failure cases are. Because if you can't define what the failure cases are and have at least some samples that you're looking at of like, it never gets when we have two shades of blue that are really close to each other, then you don't even know what you're looking for after the fine tune. So definitely start with the prompting there. And the other cool thing that we do is as you're prompting within Oxen, we're actually behind the scenes creating a little data set for you with all of those prompts. So you could go in here and grab all the ones that worked really well, take that as a subset, and then kick off your fine tune from there. So we kind of do a little magic behind the scenes as well. The other good thing to mention is if you look at the pricing on this, they had already sold a contract to do this. And if you're doing GPT image gen or you're doing Nano-Banana, it's about 40 cents per image. And so with 1.2 million images, that's about $50,000. And they wanted to get this budget under 10K for their client. Um, let's see. He also listed out some of the quality issues just from prompting to dive a bit deeper into that. So it hallucinated keyholes that weren't there. This is just like a Slack message that he sent me. Small objects were a challenge. The colored parts of the workbench that weren't supposed to be turned a different color would turn a different color. So like a chrome handle that should have stayed chrome would be turned to like the frame color. Losing small details like the holes and tracks, and then text looking weird or like blurry keyholes. These are things that he said if we can get to 90% accuracy here, then we can have like some people come in and Photoshop and tweak those little things. But like these base models are hovering around 50%. That's just going to be like way too much work to kind of do the last mile. And even when setting up the initial training data set, did a bunch of sampling, did a bunch of prompt engineering to get those first couple hundred examples. Then they passed those off to some contractors to fix the blurry keyholes or fix the text in Photoshop just to get like a really crisp training data set. And so I'll give you another image that was like one of the hard ones for them. Um, when you have two colors that are really close to each other, like specifying that in the prompt is hard to do. And if it's not following the color palettes, which it seems like the base models weren't really trained on taking in these color palettes, it just really wouldn't nail this. So you can see the prompt that he finally ended up with was change the light gray parts of the frame to strong blue. So he thought strong blue matched best to this color palette and changed the blue parts of the drawers, doors, accessories to cornflower blue. So all of the drawers in their like base images were already blue, and then make no other changes and keep all the chrome parts the same. Alex asks, how do you recommend to evaluate to find the quality issues? Did the client simply eyeball the output and say 100 images, or could we use LLM as a judge? That's a great question. For this one, it was eyeballing. So it was like he had done so many samples with the base models that he kind of knew what to look out for. I think we're getting to a point where these VLLMs are getting strong enough to be able to do some of the judgment themselves, especially at scale. Uh, and yeah, Daniel Green said RLHF question mark. I wouldn't trust an LLM as a judge for this. I think they're getting closer, but having a human in the loop is good to have. And then Casey asked about the use of hex codes or RGB values in the prompts. And yeah, that's a really good question as well. Let's take a look at the actual data set here. So this is what he ended up with. And there's a couple interesting iterations. One, all of these have RAL codes, which is like a pretty standard thing in the industry. And then each one of the colors also has a hex code. So out of those 12 iterations that he went through, the first thing was actually like specifying as much information as possible in the prompt. So if you look at this caption over here, it's like to the RAL code 5011 hex code, the specific hex code. And he found that this level of detail in the prompt was actually just like confusing the language modeling half of Qwen-Image-Edit. And the more he simplified it down and just had it learn from a starting place that it already kind of got a close color, so like strong blue or navy blue, that was a better bootstrapping point than the hex codes or the RAL codes. So that was kind of some of the iteration that he did through the training data set. Cool. So once you have a training data set, and this actually isn't the final one, let's look at his data set here. Here we go. So yeah, you can see like caption and caption simple. So caption simple has very dark navy blue instead of the actual RAL codes. Um, and so from Oxen.ai, if you have a data set like this, these data sets get these magical powers here in the Actions tab, and one of them is fine-tuning a model itself. So this brings you to a page with a few options. So we have a bunch of different tasks that you can fine-tune, from fine-tuning LLMs to image generation models, image editing models, even video generation models, which I know some people on the call here have played with. And so the one that we're playing with today is image editing. And there's a few models you can choose from: Qwen-Image-Edit or Flux Context Dev. These are open source models. And all you really have to do is pick what you want the control image to be, what you want the target image to be, and what you want the caption to be. And then also we let you put a few samples in here that you want to run during the training. So we can take that one and then have like a prompt that goes along with it. And periodically during training, um, we're able to sample these things and show you progress because it's kind of fun to watch. And we'll show you some of the outputs, the progression of the model, learning the color or learning the task in general. We hide and try to abstract away some of these advanced settings, but if you're a machine learning aficionado and like to tweak with hyperparameters, they're all in here. So the number of training steps, how long you want it to train, how often you want to sample, batch size, how big of a LoRA you want, learning rate. These are all things that are nice to tweak as you kick off jobs. And they can have different effects on the final output. Like if you have a really complex task, bumping up this LoRA alpha and LoRA rank can give you better performance, for example. And then you can kick off this fine tune here. It will go hit base 10 and start spinning up the GPUs. And Raymond, if you want to talk a bit about like what's going on in the background there, I think it'll be interesting for this technical audience.
Great, cool. One of the things we really wanted to do was make the training platform plug and play with an API. And so we've done this at the REST API layer and at the CLI layer. And so what's happening behind the scenes there is Oxen is actually invoking Base10's API, I believe through the CLI at the moment, to kick off a training job. And in this training job, you're allowed to provision storage or storage for models and data sets or storage for checkpoints. I think we're doing some pretty vanilla stuff behind the scenes here, nothing too complicated, but you basically just define the hardware that you need. And we kick off a job running in our cluster. And one of the big advantages of building training on base 10 is starting as an inference shop, we prioritized resiliency and robustness to failure in among different providers. And so big feathers in our cap are as AWS and GCP have outages, we're able to dynamically shift workloads to providers and clouds that aren't down. And so I think like when it comes to just allowing the infra to just you fire and forget, you don't have to think too much about it. Failures are very infrequent at that layer. That seems to be I think one of the biggest selling points for Baseten. And so
Yeah.
what Greg's doing is he's just kicking off this job. On my side, the job's getting deployed in one of our clusters. We're pulling the image so Greg's defined a base image and he's defined like some amount of code that he wants to run. Sweet. Yeah. So I'm looking on my side right now, and right now we're kind of downloading the image. This step can vary in terms of speed depending on whether or not the job has been ran before with that specific hardware. And so when we're thinking about the customer experimenting, if you're doing something like a grid search and firing off, let's say like 8 H100 jobs, many times that first one might take a little bit to download that image, but the next 7 are going to be almost instant to get started.
Yeah. And one of the things, so the client Allium who was doing this before, they were trying to find H100s, trying to spin this up on like the cheapest provider they would have. And sometimes the providers would have outages. Every time they spun up the machine and spun it back down, they have to like re-download their data set, reset up all the dependencies, do all of the like ML ops kind of work. And that would take up, half of his day just getting this training infrastructure set up, let alone not knowing when the job would complete. And, maybe it completed at like 3 a.m. his time. He woke up at 7 a.m. and he just paid for a GPU for 4 hours that he didn't need to. So kind of like tying the data sets to base 10's like big distributed GPU infrastructure really makes it so you don't have to think about any of those ML ops things. And it's been great for us to build on top of because we don't want to deal with the hardware half of the problem. We just want to deal with the training loop and software side.
Exactly. Yep. Just heads up that we're running now. I'm seeing logs come out for the job.
Nice. Cool. So we do the data loading part, the training loop part, and eventually, once these things finish, uh, you can see this is a big suite of the runs that Daniel has kicked off. This is one of the ones that he was more happy with. And as the model is training, so he put in a few of the difficult examples for the model to learn, and it samples it as you're going along at different iterations. So you can see this like sampled at step 85,000, 8,500, 90 or 9,000. And some of the ones that he was having a hard time to get the model learning were if the colors were really close to each other. So these like light blue and dark blue combos, or light gray and dark gray, or where there were specific keyholes that had to be in place, and we didn't want the model to hallucinate those things. So as this thing trained, let's kind of scroll all the way to the bottom to see some early iterations. You can see like the first iteration of the model doesn't even apply the frame color here, and definitely isn't following the exact color of blue that we want. And as it trains more and more, we get to the point where it's really nailing these color combinations. The next thing that we had to do was deploy this model for inference. So with the training half kind of solved with fine tuning, that's only half the battle. And a lot of the optimizations actually came in the inference optimization steps. So I want to kind of walk you guys through some of the things that you can do here, especially if you're running on your own hardware or you're deploying onto base 10. Um, and there were kind of like three steps that we took to experiment and make this model run as fast as possible. And the three steps are using torch compile, which if you're familiar with like the low level neural networks, they use a library called Torch that puts together all of the bits and pieces, the graph of your neural network. And by default, these models have some areas that they can be optimized through like a compilation step. So there's this torch compile command, and we can talk about how that sped up inference. There's methods like quantization, where you can actually take the weights that might be in floating point 16 and chop them down to like floating point 8 or floating point 4. And that allows you to fit it onto a smaller GPU. And if you can fit it onto a smaller GPU, usually those are less expensive. So if we can run a less expensive GPU for these 1.2 million images, that can cut costs down. And then finally, there's these things called Lightning LoRAs for diffusion models that reduce the number of steps that it takes to generate these images. So our hypothesis was a combination of some of these three would lead to cutting inference costs down to where we can get it under 10K for this job. And let me just get some raw numbers for you guys, so and some code that we can look at to talk about each one of these steps. So as a baseline, let's just do some math on an H100. So we have 1.2 million images. These base models take about 15 seconds to generate the images with a full 20 to 30 steps of diffusion. So if you're familiar with diffusion, we're like denoising over time. And to get higher quality, you usually need to take more steps. And so we were setting the step count to 20 to 30 to get decent generations. And so that 1.2 million images would be 18 million seconds that we needed to run. And so that's like 5,000 compute hours. And it depends on where you get your compute from. But the combination of base 10 and Oxen, it's an H100 would cost you 488 an hour for like that fully managed service. So we're looking at $24,000 if we were just doing no optimizations at all, just running this fully cooked model on an H100. So right out of the gate, we've cut it down from 50K to 24K just by switching to an open source model and fine tuning. So that's, 50% cut in savings. That's a great start, but the client really had a budget of 10K that we wanted to get it under. So that's why we started to pull out these other methods. So the first one that we dove into was Torch compile. And it's actually not too difficult to run. So if you have your pipeline in diffusers, there's kind of two main models in Qwen-Image-Edit. There's the transformer, and then there's the VAE. And so Torch has this nice torch.compile function, and you can pass in uh, different modes for it. So we passed in like max auto tune and no coup de graphs, and that this was a dynamic graph at the start. And what this does is at the very start, when you're booting up your model, you'll see your computer start cranking and start compiling these graphs together. And it takes like 5 to 10 minutes until this is like fully compiled and loaded into your GPU memory. But after it's done that, the model is much more efficient to run on the hardware. And so these two lines of code alone cut the generation time from 15 seconds to, I think it was like 12 or 11 seconds. So if you think about that, those 3 seconds when it comes to 1.2 million images, let's just do the math real quick. 12 times 18 million uh, divided by 360. Probably have to divide by 60 again. Um, we are down to, wait, is that right? No, I messed up something in here. 12 seconds. Oh, sorry, I didn't multiply that by the right number. 12. Okay. 12 seconds times 1.2 million images cuts you down to 4,000 compute hours. So that saves you a couple $1,000 right out of the gate just by using two lines of code of Torch compile. So that was the first thing we did. So that cuts it down to about 21 or 20,000 bucks. Um, the next thing that we thought would be interesting is, okay, do we actually have to run this thing on an H100, or can we quantize it and run it on smaller hardware? And so if you're familiar with quantization, I'll just show you real quick what the code looks like there. But there are different libraries like bits and bytes that will help you do this. And you can pass in the level of quantization that you want in this quantization config, and you can quantize both the transformer and the text encoder. And you could even quantize the VAE if you want, but I see people do that less and less. Um, and what was great about this is this got it down so that we could run the model on less than 40 gigabytes of VRAM. And so by default, this Qwen-Image-Edit model, it takes up 60 gigabytes of VRAM. That's why you need an H100. If you could get it down to like 40 or less, you can run it on A100, or Baseten offers these models called H100 MIGs that are kind of like an H100 split up, so that you can run more jobs than one on it. And so this quantization was definitely promising in terms of GPU usage. Uh, but the bad news was that inference actually slowed down to 14 seconds per image. So in this case, like our full time actually outweighed um, the memory savings if you just like do the math on running this model. So we really want speed over memory usage here. This is great. These quantization techniques are great if you like want to run the model locally or you just are really constrained on the GPU budget. Um, but part of the reason that quantization didn't work on these ones is Hopper H100s are only optimized for low precision if the actual like kernels under the hood leverage them properly. And a lot of the H100s work much better at floating point 16 or floating point 32 than the quantized model. I'm curious, Raymond, if you have done any
Mm.
more quantization experiments or if you have seen a similar thing with the H100s and
Uh,
FP8.
Yep, I'm going to go ahead and say not my field of expertise. There is an entire team at Baseten who has built a really incredible inference stack um, that focuses on this end-to-end compatibility and does get these end results of not only lower memory usage, but incredibly fast time to first token and throughput. To toot our own horn, today we made a release. We're running GPT OSS 120B. The fastest among anyone running it on NVIDIA hardware. So this team really does really does pull its weight for the company, and kind of we have like our own stack based on TR2 LLM, which is NVIDIA's performance inference stack. So
Nice.
can't speak too much on it, but different quantizations available, different types of speculative decoding, look ahead. I think those apply a little bit more to language models, but really meeting some intense technical requirements there.
Cool. We'll have to loop in that team because this initial experiment didn't work great for us, but I bet we could partner with them to like knock it out of the park on memory usage and on uh, the compute throughput. Cool. So then the last thing that we wanted to try was can we use what's called a Lightning LoRA here? And if you're not familiar with Lightning LoRa's, let's just look up this Qwen-Image-Edit one. Um, so this is a really cool project on Hugging Face. And what this allows you to do is reduce the number of steps that you need to do. So you can see like num inference steps here can be 8, or it can be as low as 4, depending on the Lightning LoRa that you're applying. And they have a bunch of these pre-trained LoRas here that you can just download. So you can see there's like Qwen-Image-Edit Lightning 4 steps at BF16. That's actually the one that we used because the Hopper GPUs work best on BF16. And this cut the number of steps down to 4 instead of that 20 that we were running before. But you can see there's like an 8-step one. Uh, Allium said that he played with 4-step versus 8-step. He wasn't seeing much difference in quality between them, at least for this task. I know for some other tasks where you need like hyper realistic faces or other things, you might want to go with the higher 8-step one. But the 4-step one seemed to work pretty well for this task. And if we do the math on that, we cut the time per image down to 4 seconds, which led us to 5 million seconds, about 1.5 million hours. And that's what got us actually down to this 7K, 7.5K budget. All the way, if you think back to the start, comparing that to 50K for Nano-Banana, which wasn't even consistently giving us good results at the start. We've now just like cut the cost drastically, made the model more performant, more efficient, and the quality is higher. So back to my point at the start, big fan of open models because there's no way that you could do this like through an API of a closed source model. So I'll pause there for any questions. Were there any good ones in the chat, Raymond, that you saw that you wanted to answer?
Yeah. Alex asked me a little bit about the grid search piece, and I think one of the things that the platform allows you to do really easily is fire off jobs in parallel, and so you can kind of get this signal like really soon about like what specific parameters are going to help train your model to get to like optimal performance, right? So, if you're kicking off 10 jobs and then kind of toggling through these metrics, you can easily see where your eval loss is lowest, where it's, in competition, and perhaps where it's just going to shit. And early kill those jobs, save your money, and get to a really great model as fast as possible.
Cool. I see another one asking about nunchaku, which I haven't heard, but let's pull it up here for everybody to see. Um, Nunchaku for Qwen-Image-Edit, claim 3 to 4x speed up. Yeah, I wonder if they're doing something similar to the Lightning LoRA here. Has anybody used this one? It does look like they're doing some hardware optimizations too, which is interesting. Cool. I'll have to forward this one along. Thanks for sharing that one. Instead of an 80 GB card, they have Qwen-Image-Edit running on a 4090. Nice. And 10 times the speed. Okay, cool. This is definitely something we'll look into for this project. So we're still kind of waiting on running the full end-to-end inference run, but let me give you a sense of how they are planning on doing that as well. So this is another thing that Baseten is helping with behind the scenes, and that Oxen is orchestrating. But if you have a data set within Oxen like this, one of the other magical powers you get is running models on that data set. And we have all of the models that you saw on the models page there. But we also have like image to image models, and you can select from any of those developers, or you can take one of your custom models here and train them. So these are a few custom models that I've trained. And what we do in the background here is let you specify your prompt here, let you specify the columns that you want to take as inputs, and then we'll go loop over this big data set, spin up as many GPUs as you need on the background, and kind of crank through all of these jobs in parallel. So if he was going to process these 1.2 million images on Vast AI or some of these like cheaper GPU providers, he would have to babysit all the jobs. If they ever die, he would have to go collect that data and restart it. This makes it just like a one button click. We handle all of the transformations, saving it back to your Oxen repository. And I think it would have taken like 55 days if he was just going to run this sequentially on his own hardware, and being able to scale it up on base 10 gets that down to like a two day workload. So much more efficient, much more scalable. And we kind of wired up all of that with base 10 as well.
And quick question there, Greg. Are y'all using the inference product under the hood here, or is it something like a batch through a job?
Yeah, we're using the inference product, and then you
Nice.
guys have an async inference API where
Mhm.
we can just
Yep.
like queue up everything, and then you guys manage all of the callbacks and scheduling. So that was really nice to kind of pair that together.
Sweet.
Cool. Well, I know we have got about 10 minutes left here. I'm going to kill the recording if there's questions that people want to ask offline. But thanks y'all for watching if you're watching on YouTube. And if you want to come to the live sessions, the chat's always vibrant here. And we've got really smart people who like to bounce ideas off after we kill the recording. So I will see you later.